Can you hear me, Tùng? Okay, yeah. Okay, yeah, we continue. Okay, so now we take example. Okay, so maybe we should consider this one, right? So for now, for solve the system of linear equations, okay, so you try to modify this linear system to become row echelon form. Okay, so now we say this one is R1, this one is R2. Okay, so we try to delete 6x. Okay, so that means that I apply the third rule, right? We have minus 2 times R1 and then plus R2, replace into R2. Okay, so for minus 2 times R1, you can get what? You can get a minus 6x. Okay, minus 4y, because minus 2 times 2, minus 4y, is equal to minus 4. Okay, and then you plus with this one. So minus 6x and 6x, so you get 0, 0x. Minus 4y and 4y, you get 0y. Minus 4 and plus 14, you get either 10. Okay, and here you get 3x plus 2y is 12, you know. This is 0x, this is 0y equal to 10. Okay, so this is contradictory. Okay, or we can say it's inconsistent. Inconsistent. Okay, we don't have any values of x and y such that 0x plus 0y is 10. No, no. So that means we conclude that the system here, no solution. Yeah, no solution. Okay, yeah, I hope all of you understand. Now, yeah, use elementary row or column operation. Yeah, totally we have 3 rules. Now, continue. We talk about matrices. Matrices. Okay. So for now we have the linear system. Okay. We have the linear system here. We have m equation and n rows, n variable, m equation. M equation mean we have m rows. Okay, row 1, row 2 to row m. We have m equation and n variables. Now if I just pick up the coefficient, if I just pick up coefficient, you get a11, a12, blah 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 to a1n, and then b1. We have a21, a22, blah blah blah, a2n, b2, am1, am2, amn, blah blah bn. So this matrix we say augmented matrix. Augmented matrix. Okay, so this matrix is augmented matrix. Yeah. Matrix. Okay. Yeah. So if I divide this matrix into 2 parts, okay, and this one and this one, okay, yeah. So this one we say that means I ignore b1, b2, bn. If I ignore, so this matrix becomes coefficient matrix. coefficient matrix. Why? Because we just focus on all coefficients for all equation. We skip, okay, we skip constant terms, right? Okay, so anyway, if I mention about augmented matrix, that means we also consider constant terms. If I only focus on coefficient matrix, you can skip constant term. Okay, for example, this one. We have example here, right? So the first equation we have 1, 1, 2, and the constant term is 9, and 2, 4, minus 3, 1, and 3, 6, minus 5, 0. So this is augmented matrix, right? This is augmented matrix because we are considering all constant terms. Okay, next. Okay. Yeah, example. Here we have the linear system. So if I would like to get an augmented matrix, okay, you get what? 1 minus 2 and then 1. We don't have x1, so 0, 2, minus 8, 5, 0, minus 5, and the constant term 0, 8, 10. Okay. Okay. So from this is augmented matrix, right? This is augmented matrix. Okay. So we have the observation. Okay. So if we consider the first column, this one for x1, the second column, this is for x2, and here for x3, and here for constant term, right? So that means you get 1 x1 minus 2 x2 plus 3 plus x3 is 0, 0 x1 plus 2 x2 minus 8 x3 is 8, 5 x1 plus 0 x2 minus 5 x3 is 10. Okay, yeah. And now if we skip this one, okay, we only consider this matrix, so becomes coefficient matrix. Coefficient matrix. So this one is coefficient matrix. Okay, here is coefficient matrix. Okay, we just give constant terms. So now we have two definitions, right? Two concepts: the augmented matrix and coefficient matrix. Okay. Yeah. Any questions so far? Okay, I hope all of you understand. Okay, so we have some exercise. The augmented matrix of linear system have been reduced by row operation to form the form show. In each case, continue the appropriate row operation and describe the solution set of the original system. Okay, look. I just pick up question 7. Okay, question 7. So for question 7, you can see if we would like to indicate this is constant term, right? Because this is augmented matrix. This is augmented matrix, this is constant terms. So you can get what? And this one for x1, this one for x2, this one for x3. Okay? Sorry. So for now, for the first equation, you get what? X1 plus 7x2, okay, minus 3x3 is minus 4, right? The first row. The second row, you get what? 0x1, right? Plus x2 minus x3 is 3. Now, 0x1 plus 0x2 plus 0x3 is 1. And then 0x1 plus 0x2 plus x3 is minus 2, right? So according to the augmented matrix, okay, augmented matrix, I can express the linear system like this, okay. So how about the solution? How about the solution? Look, if we consider this one, you know, this is inconsistent. This is inconsistent. Why? Because 0x1 plus 0x2 plus 0x3 we cannot get. We cannot get. Okay, one. So I say that here we have no solution. Yeah, finish. 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 Continue. Number 8. Number 8, we have, you know, this one for x1, x2, x3, and this is constant term. Then you get 1x1 minus 4x2 plus 9 x3 is 0 and 0x1, okay. 1x2 plus 7x3 is 0. And then 0x1 plus 0x2 plus 2x3 is 0. Okay, so here 2x3 is 0, that means x3 is 0. So if x3 is 0, x2 is 0, x2 and x3 is 0, so x1 is 0. So you get the solution is what? The solution is on 0, right? Do you understand? Here, this is 0, skip it, so 2x3 is 0, that means x3 is 0. If x3 is 0, 1x2 is 0, so that means x2 is 0, x1 is 0. Okay, so we can get this one. We get this one. Okay. Any questions? And then to continue, yeah, for the others. Okay, so this one is on row echelon form. On row echelon form. So how can we recognize we get row echelon form? Now look. If we consider this equation, okay, so this is the leading entries. This is the leading variable, right? Okay, this is leading variables. Okay, and this is leading variables. Okay, later on we will discuss about leading variable, leading coefficient, leading entries. Okay, so now this one lie steps. Okay, or row echelon form. So you get the result very quickly. Okay, now and the others for your reference. Okay, you answer for yourself. Now examples for final exams questions. So the final exam, I will give you some questions like this. Okay, the augmented matrix of linear system has been transformed by row operation into the form below. Determine if the system is consistent or not and explain your answer. Okay, yeah. So, okay, how can we get the answers? Okay, look. So here we have x1, x2, and x3. This is a constant term, right? Because the matrix is augmented matrix, so this is constant terms. So you can get 5x3 is 0, mean x3 is 0. If x3 is 0, x2 will be 0. Sorry, x2 is how many? Okay, you need to calculate, you know. Yeah. So you get 4x2 minus 7x3 2 and x to 0, so you can get x2e half, 2 over 4 you get half, and then 1x1 plus 5x2 plus 2x3 is minus 6, x is 0 and it's 5 over 2 equal to minus 6. So that means you can get x1 is minus 6 minus 5 over 2, you get minus 17 over 2. Okay, so this is consistent. This is consistent. This system is consistent because we have the solution, right? We have only one solution. x1 is minus 17 over 2, and x2 is 1 over 2, and x3 is 0. Yeah, okay. I'm correct. Here you get minus 17 over 2, x2 is 1 over 2, so you get 5 over 2, and you plus x3 is 0. Okay, so minus 17 over 2 plus 5 over 2, you get minus 16 over 2. Sorry, minus 10 over 2. 10 over 2 is minus 6. Okay, correct. Okay, yeah. So the answer is the system is consistent because we have the explanation here. Okay. The next one is 3, 4 minus 2, a solution of the following systems. Yes or no? You should explain. And for what values of x and k is the following systems consistent? Okay, so we need to determine x and k in such a way that the system here is consistent. Okay, so very easy, you know. So here I just explain to you here. Okay, what values of x and k in the following system consistent? Okay, so now we have the augmented matrix, right? Augmented matrix is what? 2 minus 1 x minus 6 3 and k. Okay, this is row 1, this is row 2. Okay, so I would like to delete minus 2x1, so minus 6x1. This is R1, right? This one is R2. So if I times 3 with R1, and then I plus R2, break into R2, you can get what? I times 3, so here I get 6x1 minus what? 3 to 6x1 minus 3x2 e 3x. Okay, this one left this one, ignore this one, but this one disappear, so you get what? So we can get 0 0 and then 3x minus k, right? 3x minus k, and here you can get what? We just rewrite here. You can get 2 minus 1 and x. Okay, so now we consider this one. Okay, so this one is consistent. This one is consistent if and only if 3x plus k to be 0. Okay, to be 0. That means k is 3 minus 3x. Okay, or x is minus k over 3. X is minus k over 3. So if we have the condition x is minus k over 3, this system is consistent. For example, if we have ke1, what's ax? Maybe ke3, right? If we have ke3, x is minus 1. Okay, so the condition here, okay, so the condition here to make this system, the linear system, to be consistent. Okay, now you can check. You can check if Ka3 here, if Ka3 equal to 3, and then x is what? Xe minus 1. Okay, yeah. So x is minus 1. Okay. So you can get yeah, the consistency. You can get the consistency of the system. Okay. Yeah, because this one will become 0. Okay, so we have the system here has many solutions. Many solutions. Many solutions if we have the condition x is minus k over 3 or k is minus 3x. Okay, that's all. Any questions? So, you know, some final exam questions like this. Okay. No questions so far? Okay, no questions. Okay. Okay, continue. Now we talk about Gaussian elimination. Okay, so we use Gaussian elimination. Okay, to get the row echelon form. Okay, yeah. So of course we understand what's a augmented matrix, what is coefficient matrix. Okay, from a linear system, right? And if we use matrices and Gaussian elimination, okay, we can get row echelon form. Okay, so when we get row echelon form, we can apply back substitution to solve a system linear equation. Okay, yeah, and then we also study Gauss-Jordan elimination. What's a Gauss-Jordan elimination? What's a Gaussian elimination? Okay, and how to solve the homogeneous system of linear equation. So this is the content of session 2. Okay, so I summarize for you. If you would like to solve the linear system, right, we need what? We need row echelon form. So if we would like to get row echelon form, you need to apply three rules, right? Elementary operation, right? 3 elementary operations. Okay, so when we apply 3 rules to get the row echelon form, we say Gaussian elimination. Okay, yeah. So if you get the row echelon form, you can apply what? You can apply back substitution. Okay, you can get the solution. Okay, yeah. So the key task is here. We should apply 3 rules, elementary operations, to get the row echelon form. So this process we say Gaussian elimination. So when we get the row echelon form, you can get the solution. So the process we apply, the performance we do is back substitution. Okay, yeah, okay, yeah. But first of all, when we apply 3 rules, we should have what? Augmented matrix. Okay, you should have augmented matrix or coefficient matrix. Okay, yeah. So now how many steps we have? 4 steps. Step 1. I just say S1. S1 means step 1. You need to know, you need to write the augmented matrix or coefficient matrix. Step 2. Step 2. Step 2, we apply 3 rules or 3 elementary operations to get row echelon form. This is step 2. And then step 3, we apply back substitution to get the solution of linear system. So totally we have 3 steps to get the solution of linear systems. Okay? Is it clear for you? And so what is Gaussian Jordan elimination? Okay. Yeah. Now, continue. So from row echelon form, if we apply Gauss Jordan elimination, okay, elimination, you can get reduced row echelon form. Reduce row echelon form. Okay, and then we also apply back substitution. Okay, to get the solution of linear system. Okay, so if we follow, if we when you get row echelon form, we continue to apply Gauss-Jordan elimination. Okay, you can get reduced row echelon form. You know, reduce row echelon form, and then you can get the solution of linear system. Maybe you don't need to apply back substitution because when you get reduced row echelon form, you can get immediately the solution. Okay, but anyway, so this is step 4. It's just you know, just extension. You know, this is step 4. Okay, so you can go this way, right, to get the solution of linear system, or you can go this way to get the solution of linear system. It's up to you. Okay, so it depends on the question, the questions in the final exam I give you. If I just ask you to apply Gaussian elimination to get the solution of linear system, you follow this way. Okay, yeah, you follow this way. Or if I ask you to apply Gauss-Jordan elimination, you need to follow this way. Okay, yeah, it's up to you. Okay, yeah, sorry, it's up to the questions. Okay, so if I will not say anything, so it's up to you. You can apply this way or this way. Okay, now go detail. Okay, so you know why we apply Gaussian elimination, right? Because we would like to get row echelon form. Row echelon form. Yeah, because we would like to get row echelon form. So okay, so we should know what is row echelon form. Look. In the definition, we have some definition, you know, a non-zero rows or columns in a matrix means a row or column that contains at least one non-zero entries. Okay, so now we have the definition of non-zero row or column, right? Again, a non-zero rows or column in a matrix means a row or column that contains at least one non-zero entries. Okay, so this one, you know, we don't have zero row, you know, because we have entries. What does this mean, entries? Okay, we can say this element or we can say this one the entries. So a leading entries, the second concept, the leading entries, okay, or the leading coefficients, the same. The leading entries are the leading coefficient of a row refer to the leftmost non-zero entries in a non-zero row. Okay, so if we consider this one, okay, this is the leftmost, right? So 2 is the leftmost. Okay, so this is the leading entries of the first row. This is the leading entries of the second row. Why? Well, we cannot consider zero, you know. Look, the leading entries of a row refer to what? Refer to the leftmost non-zero entries. It is zero, okay? So no. So 1 is the leading entry of the second equation, of the second row, and 5/2 is the leading entries of the last equation. Do you understand? Yeah. So you need to make sure you understand what's a non-zero row, what's a leading entries or coefficient, okay, of each row. Okay. Yeah. So if you understand clearly these concepts, continue. A rectangular matrix is in the echelon form or row echelon form if it has the following three properties. You know, we need to satisfy on three properties. The first one, all non-zero rows are below any rows of on zeros. Again, all non-zero rows are above any rows of on zeros. Okay, so here you know, here, for example, um, if we skip this one, you know, this one is zero row. This is zero row. Why? Because all entry are zero. Okay, so all non-zero row, that means R1, R2, and R3. So row 1 and row 2 are above R3. They are non-zero row certified. Okay. Each leading entry of a row is in a column to the right of the leading entry of the row above it. Okay. Each leading entry of a row is in a column to the right, of the leading entries of the row above it. Okay, so if we have R1, row 1, this is leading entry. So for leading entry of R2 should be at the right side of up to. Okay, this is the right side. The right side. Okay, and number 3, on entries in a column, on entries in the column, below a leading entry I0. So look at this one. Okay, this one. So if this is the leading entry, so on entry below 2 should be 0, right? This is the leading entries of the second equation, so the entry below 1 should be 0. Okay, so now you have 3 minutes. Try to understand the properties. Okay, before we continue, 3 minutes, please. If you have any questions, ask me. Okay, so I hope we have some questions. I don't quite understand the second properties. Okay, so I will explain to you again. Maybe I will explain by Vietnamese to help you understand. Ở cái đặc tính số 2 này họ nói là gì? Mỗi cái leading entries của một cái hàng nó phải nằm ở một cái cột phía bên tay phải của cái leading entry ở cái hàng phía trên đó. Hiểu không ạ? Như vậy nếu mình thấy cái thằng số 2 này nè là leading entry của cái hàng thứ nhất thì chắc chắn rằng là gì? Cái thằng leading entry của cái hàng số 2 phải nằm bên phải của leading entry thằng số 1. Hiểu không ạ? Again, họ nói là gì? Mỗi một cái leading entry của một cái hàng nó phải nằm trong một cái cột phía bên tay phải của cái leading entry mà trước đó. Như vậy chúng ta thấy thằng số 2 này là leading entry của cái hàng thứ nhất. Thì ở cái hàng thứ hai thì cái leading entry của cái hàng số 2 phải nằm ở cái cột phía bên tay phải của cái leading entry hàng thứ nhất. Thì nó chính là này. Okay, in English, okay, each leading entry of row is in a column to the right of the leading entry of the row above it. Okay, so this is the leading entries of the second row. Okay, so of course it's in the leading entry if is will be on the column at the right side of the leading entries of the row 1, okay, of the rows above it, okay, or you just follow the right side. If here is the leading entry of the row 1, so the leading entries of the row 2 should be at the right side of row 1, and leading entry of the row 3 should be the right side of the row 2, okay, of the leading entry of the row 2, okay. I hope you understand. You understand? You got it? Other questions so far? Yes, of course. Okay. Yeah, yeah, simplicity, for the simplicity. Yeah, you can say that. Okay. Yes. Okay. Yeah, good. Yeah, good questions. Okay. Yeah, for the simplicity. Yeah, that is correct. Okay. Other questions? Okay. Good. Okay. Continue. Yeah. Now. Okay. Now reduce echelon form. Okay. So if we apply the Gaussian elimination, okay, you can get row echelon form. Now from row echelon form, we would like to get reduced row echelon form. We need to apply Gauss-Jordan elimination. Okay, so this one, if we apply Gauss-Jordan elimination. Okay. Yes. Yes. So we follow the following two properties. The leading entries in its non-zero rows is 1. You know, so if we consider row echelon form, this is the leading entries. Is the leading entries. And this is the leading entries of the third equation. So now we would like to modify 2 to become 1. 1 here, and this one is okay, maybe it's 1 here. Yeah, another one. You know, yeah, different example. You know. So now in the leading entries of the first equation, and we should modify to get 1. This is the leading entries of the second equation. This is the leading entry of the third equation. Okay, like this. Okay, and is leading ones is the only non-zero entries in its columns. Okay, that means if we consider this column, except, okay, except leading entry, the other entry must be 0. This is the leading entries of the second equation. So if we consider this column, other entries should be 0, must be 0. And here, if we consider this column, only leading entries is 1, the others must be 0. Okay, yeah. So we can get, we can get reduce echelon form. Okay, so from here, look at this one for row echelon form. This one for row echelon form. Okay, we have the square. The square mean leading entries, and we have the star. The star mean the star entries mean have any value, maybe 0 or non-zero. So if you consider this one, the leading entries of this is the first row, R2, R3, R4. This is the leading entries of R1. This is the leading entries of R2. And here, this is on 0, so we don't have the leading entries of R3 and R4. Okay. Now, this is 0, so cannot be leading entry. So here is the leading entries of the first row, row 1, row 2, row 3, row 4, row 5. So this is the leading entries of row 2, leading entry of row 3, leading entry of row 4, and this is the leading entry of row 5. Okay, 0 cannot become the leading entry, you know. Leading entry, come back. Leading entries refer to the leftmost non-zero entries. Okay, non-zero entry. So 0 cannot become the leading entry. Now, look at this one. Reduce echelon form. This is the leading entry, and the leading entry must be 1. This is the leading entry. Here, no leading entry. Okay, so we need to modify the leading entry from non-ones to become 1. Okay, 1. Okay, it's just 1, 1, 1, 1. And remember, in the same column, only leading entries is 1, the other will be 0. The next column, the leading entry is 1, the others entries will be 0. The same, the same, the same, the same, the same. And the same column, only leading entries to be 1, the other will be 0, because we are considering reduced echelon form. Okay, example. This is reduced row echelon form. Reduce, right? Yes or no? Now look, the first equation, this is leading entries become 1, leading entry, and at the same column, right? At the same column, here is 1, the other will be 0. Yeah, okay. Yeah, so this is reduced echelon form. Reduced echelon form, 1, 1. Okay, so this is reduced echelon form. Okay, and here, no, on 0. Okay, on 0. So this is a special case. This is the special case. If we have all zeros like this, they are also reduced echelon form. Okay, and the following matrices are in row echelon form, not reduced echelon form. Now this is the leading entry, leading entry, leading entry, and at the same column, you know, here is 4. That's okay. We don't need to get for to delete 4 to become 0, because this is row echelon form. So in the same column, we also have leading entries and non-zero, the other non-zero entries. This is 1, 1. So this is row echelon form. The other, on entries, on entry below the leading entries must be 0. Must be 0. Now here the leading entries on entries below 1 should be 0. Leading entry. Okay, so now you understand this a reduce row echelon form And this one is just a row echelon form. Okay, so yeah, we finish the lecture today. We stop at the slide 34, and see you. I remember see you Friday morning for this course, right? And yeah, of course, Friday morning this is face-to-face class. Okay, I will come to the classroom. Okay, and okay, now this is the time for today, and you have 30 minutes. 30 minutes to ask TA room 340 and finish at 4 to 10. Okay, you can ask about the homework of lecture 1 part 1, or you can add some questions in relation to the content today. Okay, it's up to you. Okay, yeah, so so far any questions? Any questions? So if you have no questions, we finish the lecture today. And now the time for today, please. Okay, thank you very much. Okay, see you next class.